We're going to take a look at another optimization problem. This time we're going to do everything in one video, all steps at the same time. Let's read this question together. It says an offshore oil well is 2 miles away from the shoreline. Now I'm going to go ahead and underline that so that we can keep that in mind when we draw our picture. Okay, let's keep reading. The refinery is another 4 miles down the shoreline. So once you go 2 miles into the shoreline, then you have to go 4 miles down to get to the refinery. So let's underline a couple more things here. We do have a refinery, okay, and then we have our oil well. So if you know anything about how these things work, sometimes you have to drill oil out in the ocean somewhere, but you have to refine that oil so you can sell it for, say, gas or whatever. So you have to go 2 miles to the shore and then 4 miles down to the refinery. Let's read this. If laying pipe in the ocean is twice as expensive as on land, so underlining that. Now, why is that important and what does that actually mean? Well, in other words, it's costly to lay that pipe that's going to be pumping the oil to the refinery. It costs twice as much to lay it in the ocean as it does to land. And the reason for that has to do with the ability to lay it in there. It's just hard to work when you're in water. It's a lot easier just to, drill a trench and lay that pipe on the land. Here's the ultimate question we want to ask. What path should the pipe follow in order to minimize cost? Again, we know this is an optimization problem because we're trying to minimize cost. We're trying to not pay that much, right? Pay the least amount in order to pump the oil from the well somewhere out in the ocean to the refinery. So we know it's optimization. We are minimizing costs. Remember, just look for that superlative. Look for that word that says the least amount or most amount, biggest, smallest, whatever. Now, this is going to entail a few more questions we want to answer. How much pipe should be in the water? Okay, then we want to ask how much pipe should be on land. At what angle relative to the shoreline should the water pipe be laid? So we have a lot of questions to ask in regards to this question. All right. Now, without further ado, let's go ahead and take a look and see what our picture is going to look like. Remember, always with any optimization problem and also related rates, you always want to draw a picture first to figure out what's going on with the problem. So that's what we're going to do. All right, so here's the picture that I ultimately came up with. Here's our oil well. If you read the question, it says it was 2 miles from the shoreline. So you're just going to go 2 miles until you hit the beach, another word for shoreline. And then it says that the refinery was 4 miles down from there. Okay, you can go back and read this question again and see that's what's going on. So, I don't know the actual path, but I do know that we need to lay some pipe in the water. We need to lay some pipe in land. So, it could be more like this. All right, it could be more like straight across. Maybe you just want to lay all your pipe in the water. But you want to be able to pump the oil to the refinery, knowing that this is going to cost the pipe in the water twice as much as the pipe in the land. So right off the bat, you can kind of see a triangle taking shape. And remember, when you're doing optimization problems, you need to know formulas for shapes. We've done tanks, both conical and rectangular prisms. We've also looked at a triangle problem with ladders. So in this case, we also have a triangle. And, we've labeled everything. Here's our water pipe. Here's our land pipe. Here are our distances we're dealing with. Here's the well, and we need to pump it to the refinery. So a good picture, as I've said before, is thorough and includes all the information that I gave you in the question. Okay, so now that we've drawn a picture, let's go ahead and go to step 2 and see if you can remember what step 2 was. Remember, we want to assign variables, convert words to variables. So the first thing I did was say, okay, I know there's some amount of water pipe I'm going to lay, or ocean pipe. I'm going to call that Y. Now it's going to be in terms of miles, so just keep that in mind for your units. I'm also going to have X, the amount of land pipe that I'm going to lay, this orange right here. So again, that's looks like if it were this case, well, anyway, it could be anywhere from 0 to 4 miles. Okay, so those are units. And basically, when we draw a picture for that, okay, we can see that it's going to be this kind of triangle right here. Now remember, it could be changing. It could be a 45-degree angle. It could be 0 degree if you just went straight, if you just went straight to the shoreline and came down. And then, it just depends. But we do know this. The bottom of the triangle is going to be 2, as long as we have some amount of ocean here. The length of this, again, is how much is in the water. It's going to be y. This was tricky right here to label this triangle. I'm going to talk a little bit about that. If this is 4, okay, and this is our land pipe, then we can see that the length of this, the height of this triangle, one of the legs, is going to be 4 minus x. So, in other words, let's just say this was 1. Okay, we used 1 mile of land pipe. And the length of this would be 4 minus 1. You'd be taking away this to get this length, which would be 3. At any rate, in general, it's going to be 4 minus x. Now, I did jump the gun a little bit. I said assign words to variables. Actually, I'm still on step 1, which is just drawing a picture, but we do need to draw this triangle because ultimately, in order, like I said, to do an optimization equation, you're dealing with some sort of shape almost always. And in this case, it's going to be a triangle. But this does lead us to the next step, which is, let me one here. So this does lead us to the next step, which is to determine our constraint equation. Now remember, the constraint equation does not contain the variable being optimized. What are we trying to optimize here? We're trying to optimize the cost of all of our pipe put together. Not the amount of pipe, but our cost. You can see this in the question right now. What path should the pipe follow in order to minimize cost? So cost is what we're optimizing, in this case minimizing. Our constraint equation will not contain cost, but going back to the shape we drew, this triangle, this will be our constraint equation. Why? Because it's the amount of pipe we're using. Since these two relate to each other in terms of a triangle, remember, use the constraint equation to narrow down your optimization equation. In other words, eliminate one of the variables. So we'll be using this triangle to do that. The constraint equation does not contain the variable being optimized. We will use the Pythagorean theorem, 2 squared plus 4 minus x squared equals y squared, just like that. Let's see if I can zoom in here. So a squared plus b squared equals c squared. We need to simplify this. So 2 squared is 4. When you multiply a binomial, you FOIL it, multiply it by itself. I'm not going to spend too much time on the algebra here. You can go back and pause this and read it if you want. You end up getting y squared equals x squared minus 8x plus 20. So we've related two of the variables, the amount of water pipe, which is y, and the amount of land pipe. And we are going to do that. We're going to use that to get our optimization equation down to 2 variables. So it leads us to step 3, which is to determine the optimization equation. Again, that involves what you're optimizing. In this case, you're trying to minimize the cost of total pipe. Now, here's what makes this question even trickier. The problem doesn't really tell us how much it cost. And it makes sense because it's going to vary as years go by. I think the cost of things change. For example, gas. So we're just going to say A is the cost of land pipe per mile. So let's say it costs $1,000 per mile. I don't know. Let's say B is the cost of ocean pipe per mile. In this case, we know it's twice as much. So in that case, B would be $2,000. And then C is going to be our total cost of pipe. Now, how can we come up with an equation for that? Well, if you go back and look at your, well, actually, I have to go back to your original picture. Go back to your original picture. Everybody should be able to see that the cost of water pipe total plus the cost of land pipe would give you your total amount of pipe. Cost of pipe total. So here's your equation. C, which is total cost, is AX plus BY, where A is the cost of land pipe per mile and B is the cost of ocean pipe per mile. For example, let's say you have a mile's worth of land pipe, which would be X, and land pipe is $1,000 per mile. Well, this would be 1,000 times 1, which is $1,000, plus, in this case, B would be 2,000 times the amount of pipe in the ocean. Let's say you had 5 miles in the ocean. It'd be 2,000 times 5, which is 10,000, plus 1,000 would be 11,000. Total cost of pipe. It's how much it would cost you to lay all this orange pipe right here. That'll give you some perspective on where that equation comes from. That's going to give us our total cost, which is again what we're trying to minimize, what we're trying to optimize. If laying pipe in the ocean is twice as expensive as on land, we can easily say that B is equal to 2A. B being the cost of pipe in the ocean and A being the cost in land. So we can narrow this equation down to just two variables. Now A and B are not variables, they're constants. Whenever you go to purchase this pipe, it's not like it's going to change. Whatever you pay is what you pay. So we're going to replace B with 2A since it costs twice as much to lay pipe in the ocean as it does in land. And then just simplify that. So it's going to be C equals AX plus 2AY. Now again, I said we were going to get it down to two variables. We haven't yet, but that's our goal. But we did eliminate the B. So now we just have A, X, and Y. Now again, A is a constant. That's how much it costs to lay in the land, the pipe in the land per mile. So we need to get rid of the X and Y, and that leads us to step 4. Or eliminate either the X or the Y. We're going to combine the equations. We're going to turn the optimization equation into two variables. To do that, we use our constraint, which we had before, y squared equals x squared minus 8x plus 20. It's going to be hard to get x by itself, so let's just get y by itself by taking the square root of both sides. And then we can then substitute y right here with the square root of x squared minus 8x plus 20, as we can see right here. And that way, that's because that's what y equals. That way, we do now have our optimization equation in terms of just one variable x. So the total cost of all the pipe is going to be based on just this one variable x. Again, A is a constant. It's how much it costs per mile of land pipe. Now this is kind of a complicated formula. So when we go to take the derivative, we have to be very careful when we go to find our critical points. And over here is just a note about the fact that we just have one variable because A is a constant. All right, so now leads us to step 5, which is determine our endpoints, our feasible domain. I've already mentioned this before. On one extreme, you will just drill straight to the refinery and use no land pipe. In other words, all of your pipe that's pumping from the oil well to the refinery is being laid in the water. Now you can kind of see a problem with that. It costs twice as much to lay pipe in the water as it does in land, so that might not be our best option, but that is one extreme. Okay? That's going to be part of our feasible domain. The other extreme, I'll talk about in a second. So that would make x 0, meaning we lay no pipe in the land. And if x is 0, we can just replace x with 0 in our optimization equation. And that will simplify down to 2 times the square root of 20a. If we simplify 2 times the square root of 20, we get 8.94a. So that's our left endpoint. If we use 0 land pipe, the total cost of the project will be 8.94 times however much it costs per mile of, let's see, let me make sure I'm pretty sure that's land. Yeah, A is land and B is water. So let's say it costs, like I said before, maybe $1,000 to lay pipe on the land. You would multiply that by around 9, so it'd be about $9,000 total for your total project if you consider the fact that you don't use any pipe on the land at all. It'd be all water pipe. Okay, the other extreme you will drill straight to the shoreline and use as little ocean pipe as possible. So you go straight across this way. You still do use water pipe, but you minimize the amount of water pipe just because it costs more, right? So you go basically make a right angle and then you go down the shoreline. So you'll end up using 4 miles of land pipe and 2 miles of water pipe. In that case, x would be 4. So we can plug in 4 in for x in this case instead of 0. Simplify that down to 8a. So if we go that route, we make this right angle right here. The right endpoint would be 4 miles of land pipe. Total cost would be 8a, where a is how much it costs per mile of land pipe. And again, let's say that it's $1,000 per mile of land pipe, and your total cost would be 8,000. So those are our two extremes. Remember, for step 6 in optimization, you would determine your critical points, because combined with endpoints, that's the only place where an extreme value can occur, which is what optimization is all about. So we need to take the derivative of this. Now remember, a is a constant, so you can just imagine it being a 3 or whatever. You can use the constant multiple rule when taking the derivative. In order to take this derivative, I'm going to convert the square root to 1/2, so I can use a power rule. Then I'm going to be using the chain rule for this part. This part's just going to be a, right? Because the derivative of ax is just a using constant multiple rule. So the derivative of the outside would be the outside would be this function. The inside would be the x squared minus 8x plus 20. The derivative of the outside would be move the 1/2 and then subtract 1 from the exponent. The derivative of the inside would be 2x minus 8. Putting that together, it would look like the derivative of the outside right here times the derivative of the inside. And again, like I said before, the derivative of the left, ax, is just a. For example, if it was 3x, it would just be 3. Now it's a plus, now again, 2a is just a constant, so we're just going to carry that down when we take the derivative of this using the chain rule. So it's going to be a plus 2a times the derivative of all that. Simplifying this down, this negative 1/2, we can make it positive, put it on the bottom, and convert it back to a square root. So it'll be square root of x squared minus 8x plus 20. We'll leave the 2x minus 8 on top. These 2's right here will cancel. We'll just be left with an a times 2x minus 8 on top. That will be our derivative, which represents the rate of change of cost based on what? Based on how many miles of ocean pipe we lay. Okay, per mile of ocean pipe is actually how your units would be. But anyways, so where does C not exist? Wherever the derivative equals, wherever the bottom equals 0. Now I'm not going to spend too much time on this, but you basically, it will never equal 0, okay? If you set just what's inside the radical equal to 0, you get a negative discriminant, which means it can never equal 0. It's always positive. So there are no points where the derivative doesn't exist, but we can figure out where that equals 0 by setting this entire thing equal to 0. Now in order to find where this equal to 0, we have to combine the a with this fraction. So we have to multiply the left by the bottom's denominator, both top and bottom. It's a little complicated. We get this as the numerator. We can pull an a out, and then it won't matter because it's a constant, right? What will matter is when this is equal to 0. So we're going to set that equal to 0. We are going to subtract 2x, add 8, square both sides, do some foiling right here. As you can see, this gets pretty complex, but this is just algebra. Then we're going to basically move everything to one side of the equation. So we're going to move all this stuff to the right. When we do that, we simplify it down to 44 minus 24x plus 3x squared. Let's order that in descending powers and set that equal to 0. We're going to then use the quadratic formula to solve this equation. A, B, and C just being, the coefficients, not the actual A and B we determined before for the cost per mile of the pipe. So we get a positive discriminant, so that means we have two solutions. We will then figure out that quadratic equation using the quadratic formula. we get x equals 4 plus or minus 2 radical 3 over 3. If you use a calculator and round to 3 decimals, we get x is approximately 2.845 or 5.155. Now remember our units, it's in miles. So we're either going to have 2.845 miles of land pipe or 5.155 miles of land pipe. In order to figure out the actual critical points, we have to plug this back into our original optimization equation. So we're going to plug that back into the original optimization equation based on x. We're going to plug in our 2.845 first, and we get 7.464a. We're going to plug in our 5.155. We're going to get 9.774a. Now it's interesting to note that our 5.155 that we got is not within our feasible domain, so we really wouldn't include it. It's not going to matter anyways because it's not going to optimize what we're trying to do, which is to save money. But for step 7, we do want to determine the absolute extrema by comparing our critical points with our endpoints, and we can see that when we got 2.845, we got the smallest number here, 7.464a. What that means is if we have 2.845 miles of land pipe, we will have a cost of 7.464a, where a is the cost of pipe that we lay in the land. So let's say again, going back, let's say it costs $1,000 per mile of land pipe, then our total cost would be about $7,500 total cost of the project. Now, obviously, it's going to be way more than that. Example. So from here, we can see that if we use 2.845 miles of land pipe, we will minimize our total cost of all pipe at 7.464a, where a is the cost of land pipe per mile. Step 8, determine additional information. Well, if you go back and read the question asks for how much land pipe and how much water pipe. So we need to go back and use our original triangle here, plug in 2.845 for x and solve for y. We get y is equal to 2.310, so we'll have 2.31 miles of water pipe. If you go back and read the question, it also says to figure out this angle. So at what angle are you going to basically lay the pipe in relation to the shoreline? Well, we can set this equation up using cosine. Cosine is a adjacent over hypotenuse, so it'll be cosine of theta equals 2 over y. Since we know y is 2.310, it'll be cosine inverse of that. Now we did round. I'm pretty sure that if we didn't round, you would get exactly 30 degrees back. But anyway, to get theta by itself, you would take the cosine inverse of both sides. Okay, so that's it. Now we can just read the answer. I'm going to go back and look at the picture so to give you kind of more clarification on what we just solved. But step 9 is to state the answer verbally. So in order to minimize cost, you need to lay the ocean pipe toward the shoreline at an angle of 30 degrees. You will end up laying 2.31 miles of water pipe and 2.84 miles of land pipe. The total cost of the project will be 7.464a, where a is the cost of land pipe per mile. So again, let's say it costs $1,000 per mile for land pipe. Your total cost would be about $7,500. So basically what we've determined is, we're going to have to go way back here. Okay. This angle needs to be about 30 degrees. Okay, we're going to use a little bit more than 2 miles of water pipe. And we're going to end up using, got to go back because this is such a long problem. We're going to end up using about almost 3 miles of land pipe. So we actually end up using more land pipe than water pipe, which makes sense because it costs half as much. That's it for this optimization equation. I know it took a while. I remember when I first saw this problem, I was blown away. But if you notice, a large part of solving this problem had to do with drawing an accurate picture, detailed picture on what we're trying to solve for. It just helps give context as to what you're trying to solve for, what it looks like. That's it for this oil refinery engineering optimization problem. If you have any other questions about this, let me know.